Welcome to Chem Lectures topic on purification and separation. This is the second topic of the GCE O-level chemistry syllabus, and this is quite an important topic because there will be quite a few techniques within this topic that you will need to use later on in your chemistry life. For example, filtration, distillation, evaporation, and so on and so forth. So before we begin with this topic, let's have a quick overview or just quick introduction of why we need to learn how to purify and separate things. So on this screen here, you see 5 different types of 5 different grades of water, with the stark difference being the price. Alright, so it can range from as much as $96.40 per liter to about $0.00117 per liter. This is quite a drastic change. And what actually determines the cost of this different grades of water? It's the purity. You notice for tap water it's about 1%. Actually, it varies throughout. Different countries have different levels of purity, and we go up to the higher grades towards HPLC and LCMS. These two are actually machines used for separation. You will learn more about this when you take on A-level chemistry. But the essence is that in order for you to put in a sample into the LCMS or the HPLC for separation, the water that you use to dissolve the sample, if you're using water, must be extremely pure, less than 0.0001% impurities. That's why the water is so expensive, because it has to be specially made and specially purified to reach this degree of purity. So let's start. What is a pure substance? It's quite straightforward. It's basically a single substance not mixed with anything else. So for example, if I tell you pure gold, it's basically gold by itself. If I say, let's say, Ribena. Ribena is basically water with the Ribena syrup, so this is not pure anymore because it is a mixture. So a quick example of this table salt here, is it pure or is it impure? If we look at the chart on the side, you will notice that it contains 45% iodine, which means that it is not pure because it contains sodium chloride, NaCl, and iodine, I2. So these two things make up the mixture, which gives you the table salt. And this naturally brings us to what is a mixture. So an element is something with only a single substance. So a mixture is something which is two or more substances that are mixed together. Mixing is a physical combination. That means that it can be separated without any chemical methods. It means I don't need to do something like, say, electrolysis to separate the mixture into separate parts. I can use simple physical methods which do not involve any chemical reaction. So a mixture consists of two or more substances that are not chemically combined together. For example, water and sand. This is a mixture. And as we had mentioned earlier, why is purity important? Price. The purer the substance, the more expensive it is. And as you proceed on to doing chemical reactions in the lab, your extent of the reaction means how much the reaction progresses to completion, the efficiency of a reaction, how much of your reactants are converted into the products, actually depends on purity. If you have impure chemicals, usually these two will give you quite bad results. The efficacy of a chemical, for example, drugs. Let's say you take a medicine. The medicine is 80% pure, 20% contains impurities. That would be pretty bad for your health, and I don't think it will be as efficient as efficacious or as effective as a drug which is 100% or 99.999% pure, right? Okay, so for this topic, you will need to know 8 main types of separation techniques, of which actually 2 are pretty similar, and one of them is actually used almost every day in your life. So let's start with the first one. Decanting is quite simply the pouring away of the water from an insoluble solid. For example, when you wash rice with water, you have your water and you have your rice. How do you get rid of the water? You simply pour away the water. You pour the water out of your rice pot. So this is called decanting. This is not actually a very good way of separating two different substances. For example, if I have a beaker of water with sand, and I were to say that, okay, I will decant off the water and you can drink this water. Would you drink the water? Not really. Why? Because the sand will contain other impurities, and these impurities will get into the water here. So it is not exactly pure water. It is just decanted water. So another example, chicken soup. Chicken soup in a pot, if I were to pour just the soup, this is also called decanting. Filtration is another common technique which uses a piece of filter paper, and it can only be used to separate an insoluble solid from a liquid. How so? How so? A filter paper is simply a piece of paper which looks like this when it is folded. If I were to pour in a mixture containing a liquid and a solid, only the liquid comes out. Only the liquid comes out, and the solid is trapped behind. So why is the solid trapped behind? It's simply because the filter paper actually consists of many tiny holes. So if I were to magnify the holes like that, let's say I now have water and I have my solid. So it is quite obvious that the solid particles here will be stuck. It cannot go through the holes here, or what we call pores. It can't go through the pores of the filter paper. Only the water is allowed to flow through. So this water which flows through is called the filtrate, and whatever remains behind in the filter paper here is called the residue. Evaporation is another common technique used. It is used to separate dissolved solids from a solution. Quite simply, this example, salt. So how do you get sea salt from seawater? Simply evaporate off the water, and what you have left with is the salt. So this is an example of a commercial salt mining farm, where they have all the salt, all the seawater in pans here. They are allowed to evaporate off. The sun evaporates off the seawater, and what's left behind is the salt, which is scooped up, washed, and then packed for sale. But this is not a technique which can be used for everything. Not all soluble substances in water can be evaporated off. For example, sugar. If you were to evaporate off water from sugar, you will end up with burnt sugar. You won't get back the sugar. Okay? Right. So let's do checkpoint 1 now. Try not to see the answer here first. Attempt checkpoint 1, and we will continue. Okay, checkpoint 1 basically has a mixture of iron filings, salt, and sand. So how do you separate these three different substances? Quite straightforward. Number 1, we get rid of the iron filings with a magnet. Number 2, we have salt and we have sand. We know that salt can dissolve in water, so we dissolve the salt in water. We filter out the sand. And then we evaporate off the water to get back the salt. The next technique that I'll be elaborating on is crystallization. So crystallization basically involves you getting a dissolved solid out from a solution when you cannot use evaporation. Okay, when you cannot use evaporation. So a good example of crystallization, a good example of a separation procedure which you can use crystallization for is sugar water. So you cannot evaporate off the water and get the sugar back, but you can crystallize the sugar out of a sugar solution. So how do you do that? It's actually quite straightforward. So first of all, you have to obtain what we call a saturated solution. So this is the saturated solution. So how do you get the saturated solution? You must first dissolve the substance in a solvent. So let's say we have sugar and some dirt. We don't know what's the dirt. Let's say this is just the impurity. So first of all, we dissolve this mixture into water. Then we filter off any undissolved substances. There may be some other parts of this impurity which can dissolve in water, but we don't really need to care about this. We just need to make sure we dissolve whatever we need into the water. So now with this mixture with this solution over here, we evaporate. So what does this evaporation actually do? When you evaporate the water, you actually make it into a saturated solution. So let's illustrate this with a very simple example. Imagine this is a beaker, and these are all my water molecules. Alright, so as I dissolve in my substance is X. As I dissolve in my substance, it will look like this. So notice that there are spaces between the water molecules where my substance X can recite. So what evaporation to saturation does is simply to remove away water molecules. And as I remove away water molecules, there will come to a time when there is not enough space between the water molecules for my X to recite. So what happens? When there's not enough space, the X basically pops out. It comes out of the solution, and X, when it comes out, it clusters together and it gives me what we call the crystal. Okay, so this is what we call the crystal. So as I mentioned earlier, first we dissolve, then we filter, heat to saturation, and then we just leave it to cool. So why does leaving to cool let the crystals appear? So same thing, recall earlier, the solution is now like this. Saturated is when I can no longer dissolve any more substance into the solution. So let's say this is the maximum number of X's which can be dissolved in the water. So and this is the saturated solution. So as I let it cool, what happens? The water molecules come closer together. So as they come closer together, the X has less space to be accommodated between the water molecules. So if it has less space to be accommodated between the water molecules, it simply comes out of the solution and it clusters together, and this gives me the crystal. So this is basically how crystallization proceeds. Okay, so once we have the crystals, of course, it is not just there. We don't just stop there. We have to filter the crystals out. The crystals now become solid. They are the solid part in this mixture. So we filter out the solid crystals. We wash it a little bit with some cold distilled water. Why must it be cold? Because we don't want to dissolve away too much of the crystal. We just want it to get rid of any other impurities that is on the surface of the crystal. And thereafter we press dry on filter paper. Or we can just say leave it to dry. Okay, so this was explained earlier. Basically, summarize it. The solubility decreases as temperature decreases. So whatever that cannot remain dissolved will come out as crystals. The same picture here. So my solvent, you can take this as the water molecules. This is the dissolved substance. As the solvent particles come closer and closer together, there's less space for the solute. So they all come out and they cluster together to form the crystal. The next separation technique is sublimation. This is seldom used actually. It is only used when you have a substance which can actually sublime. Sublime is basically the change in state from solid to gas without going through the liquid state. So for example, iodine sublimes. So if I have a mixture of, say, iodine and sand, if I heat this mixture, the iodine will sublime off as iodine vapor, and then I can collect the iodine by cooling it on a cold surface. Should also know that ammonium compounds can also sublime. This is dry ice. Dry ice is solid carbon dioxide, CO2 solid. It also sublimes. It doesn't undergo a liquid state, at least not under typical conditions. Okay, so we move on to the next method called simple distillation. There's simple distillation and there's another distillation which we call fractional distillation. The difference which will be quite obvious later on. So basically we want to distill out a liquid. We distill out a liquid from a solution. So let's say we have a sample of salt solution here, salt solution. The salt maybe could be sodium chloride, and we want to obtain the water from this salt solution. So how do we get the water out? We can place it in a distillation apparatus. If we want to collect the salt only, we will use evaporation. We will just get rid of all the water, we will collect the salt. But now we want to collect the water. We don't want to collect the salt. So we have to find a way to collect the water which has been evaporated off. So this is the distillation setup to collect that evaporated water. Okay, so it's quite straightforward. You place the stuff into a distillation flask, you heat it, the water evaporates. It comes out, It is condensed and it drips out and is collected as distillate. Okay, there are a few key points here which you must take note of. Number one is the thermometer. The thermometer is actually the bulb of the thermometer is placed near the exit of the distillation flask here. Okay, why? Because when the water in this mixture here evaporates, it will rise up. So as it rises up, you will hit the thermometer, and you will know that pure water boils at 100 degrees Celsius. So when the thermometer here reads 100 degrees Celsius, and let's say this is salt water, we can be assured that the water which goes through this condenser and comes out as the distillate here is actually water. So when the thermometer, so I'll repeat myself, when the solution here is heated, the water evaporates, the water vapor will rise up and it will hit the thermometer. So when the thermometer reads 100 degrees Celsius, it means that whatever that is collected through this whole system here is pure water, because pure water boils at 100 degrees Celsius. The thermometer is placed at the top. It is not placed in the solution because we want to measure the temperature of the pure substance that is distilled off. We don't want to measure the boiling point of this impure liquid here. Okay. The next thing is the entry of the water. Water enters from the bottom of the condenser and exits from the top of the condenser. Why? Because this is the exit point. This is the exit point of the condenser. So in order for you to collect every single bit of vapor inside, you want this part of the condenser to be the coldest possible. That's why when the water goes in here, this is the fresh water, this is the coolest water. As it goes through, it absorbs heat from the water vapor, and when it comes out, it is slightly warmer already. So you want the coolest region to be here to collect all the vapor. That's why water enters from the bottom and exits from the top. Okay, so just now we covered simple distillation. This is fractional distillation. Fractional distillation is a higher level, I would say, of simple distillation. It allows even better separation of liquids compared to simple distillation. So what we use fractional distillation for is to separate miscible liquids. This means that liquids which can dissolve in each other. For example, vodka. Vodka contains water and alcohol, ethanol. So these two are liquids. We want to separate out the water or we want to separate out the ethanol. We will use fractional distillation. Okay, separate mixtures of miscible liquids with different boiling points. So this is a typical fractional distillation setup. You notice the only difference is this thing here, which we call the fractionating column. So the fractionating column is basically to allow better separation. It allows better separation. So I have water and ethanol here. We know that the boiling point of ethanol is 78 degrees Celsius and the boiling point of water is 100 degrees Celsius. So when a mixture of water and ethanol is heated, the ethanol will evaporate first. It will rise up the column. And then it will exit from the condenser and it will be collected over here as distillate. Okay. So again, the thermometer is placed near the exit. Why? Because we want to measure the vapor. We just want to measure the pure vapor. We want to measure the temperature of the vapor that is escaping. So when this thermometer here shows 78 degrees Celsius, I know that the vapor that is escaping from here must be ethanol vapor. When the thermometer here reads 100 degrees Celsius, it means that all the ethanol has already escaped and it is now water that is coming out. Okay? So as mentioned earlier, the fractionating column here, it basically allows for better separation. How so? It provides large surface area to volume ratio for the cooling of the vapors. So imagine something like this. If I have a column here, in this column I have many beads. Every single bead acts as a mini condenser. It condenses all the other vapors which come up and only allows the single vapor with the lowest boiling point to go through first. So when I heat water and ethanol, both will evaporate. Ethanol boils at 78, water boils at 100, but both will evaporate because evaporation occurs at any temperature. But what is so special about this column here is that when my water and ethanol rises up, this column here will condense everything. So what will condense first? water will actually condense first, followed by ethanol. So this process continues. So water is condensed, ethanol goes up, water is condensed, ethanol goes up, water is condensed, ethanol goes up. Eventually, when it hits the top, you get almost only ethanol vapor. And this ethanol vapor will then enter into the condenser to be collected as distillate. So if I were to chart the whole progress of the reaction out, it will look like this. Temperature will rise as I start to heat, and there will come a time in the thermometer at the top will register just 78 degrees Celsius. This means that my ethanol is distilling off. And when I see the temperature start to rise, it means that all my ethanol has distilled off, and it is time for me to collect water, 100 degrees Celsius. So you notice there are 4 main segments, A, B, C, and D. So part A, this is the heating step. Temperature rises when it is heated. Part B, temperature remains constant as the ethanol boils off. Okay, temperature remains constant as the ethanol boils off. Part C, all the ethanol is gone. It has completely distilled off. So now temperature rises again until it hits the boiling point of water. And then water will start to boil off. Okay? So the next question which brings me to is, why is part B and part D flat? Why does the temperature remain constant? This is because when you are heating, the energy is transferred to boiling off the substance. So the heat transferred in is used to boil off the substance, which means that effectively there's no net gain in heat because the substance is being boiled off. So when you boil off a substance, the heat energy is also removed at the same time. That's why it remains flat. So temperature remains constant. Temperature remains constant at these two junctures, B and D. Some commercial uses of fractional distillation, the most important of which is the refining of petroleum or crude oil into the various fractions like petrol, diesel, and so on and so forth, and to produce ethanol to make your alcoholic drinks. Fractional distillation of air is also quite an important process. It allows you to obtain pure oxygen for use in, let's say, hospitals, pure nitrogen for use in chemical reactions, cooling facilities. This is an aerial view of Pulau Bukom Island. This is one of the Singapore offshore islands, Pulau Bukom, where there's a huge Shell refinery here. So you notice all these little white dots here, they're all the storage containers for all the refined fractions of the crude oil. Okay, so let's attempt checkpoint 2. Take a few minutes to do this. Right, so we need to, let's see, we need to obtain potable water from seawater. Potable water means water which is drinkable. So how do you get drinkable water from seawater? We identify that this is actually salt plus water, and we want to get the water, so we have to draw a simple distillation setup. So you can follow the simple distillation setup that is shown earlier in the video. Right? So we can't filter. Why? Because the salt particle, sodium chloride, will just simply pass through the pores of the filter paper. Okay, so next question is, during the fractional distillation of air, we have these various components here. Which one will be distilled off first and which one will be distilled off last? So quite simply, we can just observe the boiling point. The lowest boiling point one will be distilled off first, which means that neon will go first, followed by nitrogen, then argon, then oxygen, then krypton, then carbon dioxide. Lowest to highest. Alright, now we have this liquid mixture containing methanol and ethanol and water. You have 3 different components with 3 different boiling points. So how do we draw the fractional distillation graph? It's quite straightforward. This is time in seconds or minutes, up to you. This is temperature in degrees Celsius. And we have 3 points, 65, 78, and 100. So temperature rises, hits a plateau at 65. It rises again, hits a plateau at 78, and it rises again, hits a plateau at 100. So we have 3 key points: 65, 78, and 100. remember to join these 3 dotted lines here. This is important. Okay, this is important. Alright, now we move on to chromatography. Chromatography, as the term says, chrome is basically color. Graphy is basically a technique. So this is a technique used to separate mixtures. Last time it was used to separate colorful mixtures. In fact, you can separate colorless mixtures. So the term really doesn't explain fully what it is used for, but basically it's a method to separate and identify mixtures of substances. So I'll show you a picture of this. This is an example of a chromatogram. The chromatography technique will give you a chromatogram. So this is a chromatogram of common food dyes. So this is 1 food dye, 1 food dye, 1 food dye, 1 food dye. So to your naked eye, it may seem that maybe, let's say, this dye is actually blue dye. But when you do a chromatogram, when you do a chromatograph, you realize that actually this blue dye consists of red, a bit of yellow, and mostly blue. So it's not just pure blue. There's some yellow and there's some red inside. Some red dyes inside this blue dye. There are different types of chromatography. The most common of which we will use in O-level chemistry is actually paper chromatography. As you move to higher level chemistry, you will start to use thin layer chromatography. This is called TLC, HPLC, and LC. So liquid chromatography, high pressure chromatography. So all the different methods of chromatography. The most common which you'll be using is paper chromatography. Why? Because it is easy to do and it is cheap. This setup here, in its entirety, would probably cost about $16,000 or so, compared to, say, you use filter paper. A box of 100 probably costs about $5. Okay, so what do we use chromatography for? Actually, it's quite evident from this picture here. You can see that you can separate this blue dye into its individual components. So we can separate and identify what is present in colored substances. But must the substance be colored? No, not necessary. We can also separate colorless substances as well. We can separate drugs. We can separate a drug into its separate component, into its individual components to see what is inside the drug. We can separate stuff such as blood, urine. In fact, the Olympics and all the major competitions, all the blood samples which are collected from athletes are all chromatographed. And the chromatogram can be used to identify any illegal drugs inside. So imagine that there's an illegal drug, so there would be one extra spot. Okay, to simplify, if I were to have one spot of blood here, and if this is normal blood, 2 spots, and let's say this is a spot from a banned substance, and this dot appears in the chromatograph of an athlete, it means that this athlete has been using the banned drug. But of course, this is not as simple as this. Right? They actually use the machine here to separate. So what you see are actually peaks like this. So maybe this peak here represents a banned drug. And if this peak is found in the blood, it means that the athlete has been doping. Okay, this method is good because you only need a small sample. You don't need like 1 liter of substance to be chromatographed. You just need 1 single drop, or even much less. And at the end of the day, you can actually recover the sample. You don't destroy the sample in the process. How is it recovered? It depends on what method is used. So let's say we use the simplest of chromatography, which is paper chromatography. We have this blue dye here, which is separated into 1, 2, 3 different components here. So how do we get this first component out? We simply cut the paper off here, and we immerse this paper into a suitable solvent, and then the solvent will dissolve the color, this dye, out of the paper. So this is how we recover the components. So how do we do chromatography? So step number 1, of course, will be to dissolve the dye in a suitable solvent. So let's say we have a bottle of dye. So this is my dye. How do I find out what parts, what different components are there in this dye? Number 1, I must dissolve this dye in a solvent. Okay. So after I dissolve the dye in a solvent, I will put a drop on the pencil line near the bottom of a strip of filter paper. So I have a filter paper here. I will draw a pencil line, and then I will put 1 dot here. Why is this pencil line drawn? It's because later on, when it is separated, the dye may split into various parts, and we will need to take some measurements. So to take a measurement, we must know where it has started from. So this is basically the starting line. The pencil line indicates the starting line. This allows us to determine a value called the RF value. I'll elaborate more on this later on. The RF value tells us what is that particular substance, because different substances have different RF values. Okay, so after we have dissolved the dye in a suitable solvent, drawn the pencil line, place the spot here, what we do is simply dip the filter paper in the solvent, making sure that the pencil line is above the solvent level. Okay, we must make sure it's above the solvent level. You cannot put it under the solvent level, otherwise the spot will simply dissolve in the solvent. Okay, you must put it above. So the paper will basically suck the solvent up. And as it sucks the solvent up, this spot here will dissolve further, and then they will move up the filter paper depending on its solubility. So if it's more soluble, it moves faster, so it ends up higher. If it's less soluble, it moves slower, ends up lower. Okay, so the solvent will continue to rise until it eventually reaches the top, and then we stop the experiment. Okay, so as I said, the pencil lines allow us to see the starting line, and the solvent level being below the pencil line is to prevent the dye from dissolving into the solvent. We want the dye to go up the paper, we don't want the dye to go into the solvent. Okay, so this is the more important part. How do we interpret this data? So the key thing is the same substance will travel by the same distance up the paper. Okay, the same substance will travel up the paper by the same distance. So if let's say I have this spot from a colored sweet, and it gives me 1, 2, 3 spots here, 1, 2, 3 spots here, and I have 3 other spots which I confirm are pure. So this is pure green, pure blue, and pure red. So the pure green gives me 1 spot, the pure blue gives me 1 spot, the pure red gives me 1 spot. And this is the spot from the colored sweet. So when I observe this chromatogram, I know that in the sweet, it contains this green color, same level. It contains this red color, same level. But it doesn't contain this blue color because this is a different level. So maybe let's say these 3 are approved food dyes. It tells me that there are 2 approved food dyes, and there's 1 food dye here which is unknown. It may be something which is not approved for use in sweets. Okay, so chromatography allows us to differentiate and separate and identify what is present in the substance. So I notice 1, 2, 3, but only 2 are legal, 1 could be illegal. Okay, so the dyes which we use to compare are known as standards. Standards basically because I know this is what it is, so I call this the standard to compare something against with. Right, so these 2 are correct, confirmed against standard. This one is not confirmed against the standard. So this one cannot be identified. Okay, the last one cannot be identified because it is not the same as the standard. So which brings us back to the pencil line. RF value. So let's say this is a piece of filter paper, this is the pencil line, this is the initial spot. At the end of the chromatography process, this is the spot here. So how do I calculate RF value? And why do I need to calculate RF value? So assuming that this spot is dye A, and the solvent which I use is water. I know that if I use water and it is dye A, the spot will always travel, say, 10 centimeters up the filter paper in the duration of, say, 30 seconds. Okay, so it gives me a value which we call the RF value. So let's say this RF value is equals to 0.7. So how do we confirm? So now this is the value we have for water. For dye A dissolved in water traveling up the filter paper. So now I have an unknown substance which I think could be dye A. How do I confirm if it is dye A? So it's quite simple. I dissolve this substance in water and I put it on the filter paper and let it run up, and then I measure the RF value. So RF value is basically the distance traveled by the spot. We measure from the center of the spot. So this is to to the distance travelled by the solvent. So at the end of the experiment, the solvent will have travelled up the paper. So this distance here is the distance travelled by the solvent. So if I call this A and I call this B, my R value is simply A over B. And if my A over B equals to 0.7, it means that this unknown spot here is simply di A. If it is not 0.7, it is not di A, something else. Okay, so quite simply, if I were to calculate the R value for the earlier chromatogram, it would be this. So this is simply A over S, B over S, C over S, and D over S. Distance travelled by the substance versus distance travelled by the solvent. So with this, I can identify the components because I can compare the R values. So the R value of this green spot here will be the same as the R value of this green spot. The R value of this red spot here will be the same as the R value of this red spot. This one and this one will not be the same. And sometimes the spot may not be visible. It's invisible. So how do we actually make it visible for us to calculate the RF value? We use a locating agent. So basically it reacts to produce a colored product. Then from this we can calculate the RF value. So this is the distance travelled by the spot. This is the distance travelled by the solvent. And RF value is simply A divided by B. Okay, so let's try checkpoint number 3. Take about 5 minutes to do checkpoint number 3. Okay, so notice that this is a chromatogram here. Sucrose, when it is boiled with acids, a reaction takes place. So some sucrose is added. So this is before boiling. So this is the original sucrose solution. You get one single spot only. So this is simply sucrose. After 5 minutes, a drop of the mixture was applied to a chromatography paper. After 30 minutes, another drop was applied. So you notice, after 5 minutes, I have 3 spots. After 30 minutes, I have 2 spots. So what does this mean? Okay, what does this mean? If you observe very closely, you'll notice that this spot is at the same level, which means that this spot is likely to be sucrose, which hasn't been broken down. This one will be new substances which has formed, probably from the breaking down of sucrose. So I can calculate the R values of these 2 spots here. So with the R value of these 2 spots here, I can compare with the R values in this table, and I can determine what are the identities of these 2 spots. So this spot here is fructose, and this spot here is probably galactose or glucose. So how do we know? Very easy. Place a ruler on the screen, measure the distance. Measure the distance of the spots. Measure the distance of the spots from the start line. Measure the distance of the solvent front, and calculate the RF values. So question number 1, why do we use a locating agent? Because we cannot see the spot. So what must you do? You must make it visible. You must make it colored. To be visible and colored. How much sucrose remains in the solution after 30 minutes of boiling? Nothing. It's gone. There's no more sucrose left. Okay, there's no more sucrose left. So how do we explain what happened to the sucrose? Basically, during the boiling, it has been broken down into its individual components. So what components are these? If you count R values, you'll notice that it will be glucose and fructose. So this is glucose and this is fructose. Okay, this is glucose and this is fructose. Right. So after learning all these different separation techniques, how do you apply it? We can one of the ways of one of the applications is to determine if a substance is pure. So if it is a pure substance, it will melt and it will boil at a fixed temperature. So pure water boils at 100 degrees Celsius, pure ethanol boils at 78 degrees Celsius. If I add in something else, it will boil over a range of temperatures. Correct? For example, my water ethanol mixture. Ethanol boils at 78, water boils at 100 degrees Celsius. If I add these 2 together, they will boil between these 2 temperatures, or somewhat slightly above this temperature. around this range. It will boil around this range of temperatures. Okay, so basically we said it melts over a range. It melts or it boils over a range of temperatures. This is a boiling point apparatus. This is a melting point apparatus. So basically inside here, you place a small bead or a small crystal of the substance, and this is the thermometer. This is a magnifying lens. You look through this one to look at the thermometer, and then you look at the substance. So once you see the substance melting, you check the temperature. If the temperature coincides with the actual temperature of a pure substance, that means the thing inside is pure. If it doesn't, that means it is not pure. So how does the impurities affect the boiling point? It's actually quite there's a simple way to remember this. Melting point is always lowered and boiling point is always increased. Okay, melting point is always lowered and it melts over a range of temperatures. Boiling point is always increased and it boils over a range of temperatures. To remember this, melting point is always the lower one. So the lower one becomes lower and the higher one becomes higher. Alright? Boiling point increases and it boils over a range of temperatures. We can also do a chromatogram. So if you remember in the earlier part of the video, when I run a chromatogram, assuming my substance is pure, I will get a single spot. If this substance gives me 2 spots, I know that this is not pure because there are 2 things which make up this single substance. Okay, so it only produces a single spot on the chromatogram. Right. So now I have 3 different substances here, and I know that this impure substance, it melts at 113. What could be the substance X? So based on the theory, melting point becomes lower, boiling point becomes higher. If it is impure, the melting point is lower, which means that originally the temperature must be above 113, so it must be nitrophenol. Okay. Next question. I have a pure dye dissolved in ethanol and I do a chromatogram. Pure dye. So what would the chromatogram look like? It would simply be a single spot. That's it, because it is pure. It will not separate into any individual components because there's only one single substance. Alright, so this comes to the end of the topic of purification and separation. The next topic will be on kinetic particle theory. So stay tuned for the next set of videos. Thank you.